So the next presentation has been given by Professor Philippou, UC Berkeley. He's going to basically, nothing to do with OpenSees. We're just going to talk about nonlinear analysis, some of the things you have to watch out for, what some of the solution algorithms are, and some of the many things he's come across over his years as professor that he's going to share with us.
Okay, so I'm glad to see you all here. Frank and I had been discussing about some kind of basic introductory lecture or set of lectures on nonlinear analysis. And I have been dragging my feet of doing that because I have a nonlinear analysis course for 28 lectures, but condensing 28 lectures down to 2 is a lot of work. In any case, under the pressure of this particular meeting today, I started working only a couple of days ago, thinking that, oh, I should be able to patch it up. And you will see that I only got maybe 1/3 through. So what you're going to see, assuming that I don't eat up my time with what I prepared, so I have 1 hour, Frank, or 45 minutes? How much will you want to give me?
Oh, you have an hour.
Yeah? No. Okay. So, assuming that you're willing to listen for an hour, I have some stuff that still looks, that is new, that I put together, trying to keep things simple, and some stuff that is sort of a patch up of some older things that I had presented here a few years ago. And what I am looking forward to hearing from you, because I know that there are evaluations at the end of this session, is if you would be so kind to be specific when you evaluate this particular lecture, so you can give me some feedback as to what we need to do so that Frank and I can go back and maybe make the lecture something that we can post as a webinar. So in the future, you can follow it, or your classmates or colleagues can follow it without having to come all the way to Berkeley, right? And that's the plan. As you will see, the lecture still misses quite a few parts that need to be inserted, and I'll point those out. All right, so I wanted to keep it very simple, as I said. I don't know if this is the right audience, and that's what you will be telling us back so that we can take it to the next iteration, so to say, right? There are not many courses on nonlinear analysis around the country. Very few places offer such a course, and as a result, I have no idea how one goes about getting the information that is necessary to conduct research in nonlinear analysis. Nonlinear analysis, in my opinion, is something that requires knowledge. Right? So if anybody told you that you are going to accept what seems to be going around in the education of the undergraduates around the world, which stems from linear analysis, which basically says that there are these great computer programs, names unknown, where all you got to do is put your model together, push a button, and get beautiful looking results. Right? If you expect that from nonlinear analysis, I think you will be seriously disappointed. Right? So the point is that without background and detailed knowledge, I don't think nonlinear analysis is for the engineering profession. Unfortunately, with the presence of software, the danger we are running is that everybody wants to push that button and hoping that things will come out. So, in any case, I don't need to tell you anything about this, but I did want to mention a few points that I convey in my classes on linear analysis and nonlinear analysis. The real structure is a complex physical object. I'm sure people told you that. The real structure is a continuum. And so in the pre-computer days, a host of methods were developed for trying to solve the partial differential equations that govern the behavior of a continuum. Up to this day, if you survey the university courses, you will see that 80% is basically spent on such a treatment. Right? So 80% of the courses are still dealing with some kind of either continuum mechanics thinking or its extension to structural analysis with all sorts of classical, so-called classical methods, whatever their names are, for solving the structure as if it were a continuum. Right? Fortunately for us, the actual structure is actually a discrete model. Computers don't analyze continuum. Computers analyze a discrete structural model. And the discrete structural model is governed by discrete relations. And so what we need to do is study discrete mechanics. Right? So you can forget all the stuff about continuum mechanics other than for deriving the relations of the element response. Once you get out of the element response, for the response of the structural model, you need to face the issues of discrete structures, discrete mechanics. And that, I don't think it is taught very well, or it's not taught at all anywhere in the world. All right, so that's the second part I want to convey with this. So for my presentations, I'd like to be sure that we understand that I make a clear distinction between elements, which are ingredients of the structural model, so they are components of the structural model, of the discrete structural model, and structural members, which of course are the sort of components of the actual physical structure. So if I say that I will subdivide a column into 4 elements, I hope you understand what I mean. Right? Everybody's kind of clear on that. So there is no reason why, for example, in a structural model, a structural member cannot be subdivided into several elements, and you will see why I need to do that. Right? So with the power of computers available today, in fact, it stands to reason that we can achieve accuracy by subdividing the structure into smaller and smaller elements of relatively simple nature, rather than complicated elements of large size. Right? So this is something you want to keep in mind. Okay, so this is an example of structural modeling that I'll start talking about with my class on Thursday. A lot of simplifications, of course, are being made in the process, right? As you see, the column of the bridges are not prismatic. And so if I want to represent a whole pier, which is of a height of close to 200 meters, as one element, I would be making a big mistake. But if I subdivide the pier into 20 elements of prismatic cross-section, constant cross-section, I could get a pretty good answer. So I don't need a prismatic frame element to represent a non-prismatic pier. I hope that this is clear. And of course, going over to shell structures or 3D structures like this cooling tower, here we have the issue of representing the surface, and we can represent the surface with plane elements or with curved elements. The same thing is true here. We can use a 2D model for certain response quantities, and then a 3D model if we're interested in a complete response. All right. So, first point I wanted to make as we go through this introduction is my insistence that we appreciate that exactly as continuum mechanics teaches, and I hope you were subjected to those kinds of courses rather than formulas that one can copy. The continuum mechanics teaches that the whole edifice of continuum mechanics is based on 3 pillars. First pillar is called kinematics, and is a relation between the strains and the displacements. The second pillar is called statics, and is the relation between stresses and forces. Forces of the element, of boundaries, or whatever. And the third pillar is, of course, the material constitution, which is the relation between stresses and strains. These are 3 independent pillars. Of course, the first 2, kinematics and statics, are related by the principle of virtual work or energy principles. And you certainly have heard that, right? So there is a very tight relation between the first 2. The third is completely independent and is the least well understood, the least well defined, the most uncertain in the analysis of structures. So a good material model is worth its number of lines in gold. All right? Gold. So be careful of that, because the other stuff is relatively straightforward. And I can set up, as you will see, templates that I can do any 2D frame element. Any 2D frame element you want, I can put a template together and you have it. But a 2D frame element that does torsion, shear, and axial force and bending moment takes a constitutive model that is robust and accurate. And up to this day, I haven't seen one that is robust, accurate, and fast. I have seen accurate and very slow, accurate and non-robust, and so on and so on. Right? So all three ingredients are sometimes difficult. All right. So, what is nonlinear analysis? I don't know. As I said, I was trying to prepare this almost like, you know, a course to an undergraduate class. So if you think that this is too trivial, as I said, you let us know, and then we take these slides out and we put them someplace and somebody can consult them, but you guys can skip over the rest. So the response of structures is governed by Newton's second law, of course. And you have the applied forces against the resisting forces. The resisting forces are dependent on displacement and velocities. Velocities are strain rates. Displacements are strains. And then we have the inertia term, and under the assumption that the mass is constant, multiplying the total accelerations. Already from this top definition, you can see, for example, that if you wanted to do multiple support excitation for nonlinear structures, like they have to do for bridges, you would have to think really hard how to do it, how to formulate. Right? So you find in books like Dynamics of Structures of Professor Chopra, you find the discussion how to do multiple support excitations for linear structures. And there are those influence vectors and all. I can derive those relatively easily from this. But then for nonlinear structures, the problem ain't that simple. Right? So you have to kind of think about how exactly to formulate the problem well. We don't do it because we don't have time to worry about this at this stage. So if the structure, so basically I am assuming here, first of all, another important point is that I am assuming here that the applied forces are independent of the deformed state of the structure. That is true for gravity, but it isn't true for wind and fluids, right? Because the fluid pressure is always normal to the surface under certain frictionless conditions. And so if the surface deforms, like the wind blows, then you have to account for P as a function of U as well. That alone would give you a nonlinear analysis situation, right? I hope that this is clear. So, for our simple purposes, we assume that the mass is constant, the applied forces are constant. Constant in the sense that they only vary in time or in the space, but they don't vary in terms of the displacements. And the only thing that is dependent on the displacement and the velocities is the resisting force vector PR. If these resisting forces are linear function of the displacements and the velocities, we are dealing with linear analysis. Otherwise, the problem is nonlinear. Simple, right? So, if they impose displacements and forces very slowly with time, by the way, I haven't said here whether I don't have imposed displacements, right? I can have displacements whose values are known and displacements whose values are unknown at the start of the analysis. So I can do multiple support excitation if I need to. But if the displacement and the forces vary slowly with time, then the equation 1 simplifies to this relatively simple set of equations, simpler set of equations, which forms the basis of all the solution strategies, including nonlinear dynamic response. Because in a nonlinear dynamic response, you discretize in time. You are left with a set of equations to be solved at any instant in time. And those equations have a look that is not quite as simple as this, but relatively similar. Independent. So I'm not going to talk about nonlinear dynamic analysis today, even though most of you probably are interested in nonlinear dynamic analysis. And that's another big set of problems, right? Because we have to deal with all sorts of things. So we'll leave that out. If you would like to see that in the lectures, you just have to say so at the end of the OpenSees days tomorrow, okay? All right. We can certainly insert something to that effect, but it won't be within an hour. Obviously, it would have to be a multi-hour lecture. All right. So, because the external forces at the restrained DOFs, in other words, DOFs whose displacement values are known, are unknown at the start of the analysis, we partition this set of equations into equations at the free DOFs and equations at the restrained DOFs. I am only going to work with the equations at the free DOFs. Right? no point of carrying these equations around because obviously I have as many unknowns R as I have equations. So if you see a textbook in linear analysis that carries this stuff around, you can toss it in the garbage can, as far as I'm concerned. Right? All they do is just inflate the size of the problem. Right? Okay. It doesn't help understanding, I think. Maybe it does, I don't know. Anyway, so the unknowns of the equilibrium equations are the displacements at the free dots of the structural model, and I use a subscript F for the free, and then a subscript D for those that are restrained or known displacements. Okay, now as far as the applied force vector is, and here it would be, I am thinking that in the future, working together with Frank, we're going to have some inserts that show you how to do some of these things in OpenSees. Right? So for example, how do you generate something like this? Right? A set of load patterns, some of you probably know that. You can always ask Frank. I think there is information online that explains to you. The applied force vector is typically supplied at the beginning of the analysis in the form of one or more load patterns that are multiplied by individual load factors, right? So you have basically the gravity load, which is constant over time, and then you have a lateral force which may be linearly increasing with time. By the way, that time t is a pseudo time, it's not real time, right? So to describe the incrementation or the change of the load factor, I need to define that in terms of an independent scalar variable. You can call that scalar variable anything you want. The typical term used in nonlinear analysis is pseudo time, because it's not real time, right? Remember, we said that the forces change very slowly with time, therefore they are not dependent. All right. So we specify the evolution of the load factors lambda. This evolution needs to be specified in some form of time series. And so you march through pseudo time, and at every instant of pseudo time, you are reading off the evolution of the corresponding load factors, multiplied by the load distribution or load pattern, and you get the total applied force to the structure at that instant in time. Right? Because this is not a trivial process to define, I encourage you to check out that indeed the applied forces are what you are thinking they are, right, before embarking on a big analysis. And I think it's needless to say, every time you try something new, you first check to make sure that the program understands what exactly you want. Right? Or rather the other way around, that you understand what the program wants to do what. Anyway, I am saying this because if you have a situation like this is a common problem I have run into with some of my students and myself and others over time. If you have a situation like this where you have more than one load pattern and you want to prescribe their evolution in pseudo time, let me give you an example. A reinforced concrete column. I'm going to apply an axial force, constant. I'm going to apply a horizontal force, increment it linearly, and then I'm going to apply another horizontal force and increment it linearly, while keeping this one constant. And then I'm going to I reverse this force, okay? That's a situation which is quite common if you are going to do it under force control. So with applied forces. That's a situation that is common in analysis. If you have more than one load factor to multiply with the corresponding load distribution or pattern, you cannot do load control. Very simple, right? Because the load factor is already pre-specified. That's a very simple case that some people say, oh, gee, you know, the structure is softening, we need to do load control. You cannot do load control if you have more than one load factor. Right? Load control is only possible with one load factor. Right? Load factor control, I mean by that. I use the name load factor control. You will see in a moment what other terminology that is being used. Okay. So if we have a single load pattern PC that remains constant, gravity, and a single load pattern and a second load pattern that changes with load factor lambda, then of course the applied forces simplify according to this way. This is a common case in pushover analysis, where basically you throw all the horizontal forces linearly incremented until collapse, right, at the same time, while the gravity is constant. And in this case, it is possible to have automatic control of the load factor lambda under certain criteria, with different criteria, right? So if you intend to analyze a softening structure, as you will see in a moment, you're supposed to be able to control the load factor lambda to track the post-peak response, obviously. To be able to do that, you need to have just a single load factor that you can control. All right, so now I wanted to spend a little bit of time. So this is basically as far as the applied loading is concerned. Now I want to spend a little bit of time on the resisting forces, and I wanted to tell you a little bit of what my philosophy is, which is shared by few around the world, and thank goodness also is shared by OpenSees. But it's something that you may not find in many other software packages. And so here I want to show you some stuff that is specific to OpenSees, that in my view is the strength of OpenSees, but you don't find in too many other packages around the world. All right, so let's talk about it. So the first part is trivial. Basically, this is undergraduate matrix analysis, right? The total resisting force vector is the sum of the element resisting forces. We are writing node equilibrium, by the way, and the element resisting forces are the end-off vector, is the end-off vector expanded to address all the degrees of freedom, right? Because the typical p, little p vector only has 6, 12 degrees of freedom. So it has only 6 components. These 6 components go inside a structure that may have 3,000 force components, because it has 3,000 degrees of freedom. To do that, you need so-called incidence array, you know that. And this incidence array maps the local degrees of freedom to the global degrees of freedom. We write this process for convenience sake as a Boolean matrix multiplication. A Boolean matrix is a matrix that only has ones and zeros, and it allows me to write the same operation that you're doing here. In fact, I should not have written PRID, so this is a typo. It should say PR of the element, not the ID. AB, because the ID is sitting now inside the Boolean matrix. The Boolean matrix multiplies the vector P, so it has as many columns as the rows of P, but it has as many rows as the number of degrees of freedom PR, global degrees of freedom PR. And with this little trick, I am able to basically sum up all the resisting forces to create the static equilibrium equations of the structure, which, as you will see in a moment, I will write as the sum of all these ABL transposes times P, right? So this is important for what's coming. All right. So now, what is special about OpenSees? And as I said, this kind of concept is shared by a few people around the world, so we are not the only ones, but few, not the majority. Actually, quite the opposite. Minority, a small minority. The concept is as follows. We are big believers in what is known as a co-rotational formulation, right? So this here is basically a 10-minute presentation of that important idea, which actually has quite some distinguished names associated with it. Argyris, Pelichko, Crisfield, Felipa, right? So these are giants of computational mechanics. But you can number them in maybe the fingers of one hand. And most other people are using things like total Lagrangian or sort of other stuff for the problem. Okay, so let me tell you what the idea is. The idea is the following. The element end forces, which I'm showing here for a 2D frame element, so that we talk simple. I can do the same thing for plates. I can do the same thing for shells. The complexity, of course, increases, and there are some issues that I don't have time to discuss here. We can talk about them some other time. if I take the end forces of the element, by the way, this is the position of the element in 2D in the original position. So this is where the element is actually located in the undeformed position. So I have 6 forces. I am relating these forces to a set of basic forces, Q. I use the name Q. You can use any name you like, any symbol you like, which we call basic forces. The basic forces are the independent forces among the 6 P's. Why are there only 3 independent forces as opposed to the 6 end forces P? Because you need to satisfy equilibrium. These forces P, acting on the element free body, need to satisfy certain relation to satisfy the element equilibrium. So you cannot pick them independently. They only have 3 independent, and the other 3 are dependent on them. The 3 independent ones we call basic forces Q. And we have a relation between the complete set P and the independent forces Q, basic forces Q, which is written in the deformed element configuration. So it is written in a system, in a coordinate system, that follows the element as it deforms. This following the element as it deforms is known as co-rotation, because the most important thing that the element does as it deforms, it rotates. The advantage of doing this is that if you see the transformation from here to this piece, you are basically you have to account is for the angle of this chord. By the way, this line that connects the 2 end nodes of the element is called the element chord. All you got to do is relate the angle of the chord during deformation and the change of length of the element. Right? These are the 2 deformation measures of a 2D frame. Now, a plate element has another set of deformations, obviously. A truss only has the change of length. Quite clear. All right. The matrix that relates Q and P, as I'll show you in a moment, actually I'm not going to prove it, I'm just going to state it, right? We prove it in courses in nonlinear analysis, is known as the transpose of the kinematic matrix, AG transpose. And this is a direct corollary, a direct follow-up from the principle of virtual warp. That's why it has to be this way, right? Incremental principle of virtual warp. All right, so AG is the kinematic matrix. I'll show you in a moment what that means. And this kinematic matrix accounts for large displacements, U, in which case we talk of nonlinear geometry. Actually, we should say nonlinear kinematics. But you will see why, for me, nonlinear kinematics is really nonlinear geometry, because it doesn't make sense to do nonlinear kinematics and do linear statics. That doesn't make any sense. So we define, once AG is a function of U, we are talking about nonlinear geometry. By contrast, if AG is not a function of U, why? Because the U's are very small displacements, then we talk of linear geometry, or linear kinematics better. Because as you will see in a moment, we can have nonlinear statics in that case. All right, so here I'm a little sloppy. I'll try to correct this, maybe add another page and be a little more specific. I think this is a little superficial here. It needs a little elaboration. All right, so too little time to explain this picture, but essentially as the element moves in the plane, because it's a 2D element, right? The actual frame element moves in space, and we have large rotations and large displacements, and the large rotations are a pain, very hard to track. As the element moves in the plane, we have this rotation beta of the chord, the change of length, ln minus L, L is being the original length, and these 2 deformation measures allow me to define 3 element deformations, which are the change of distance between the nodes and the angle between the chord and the tangent at the 2 element ends. this suffices to uniquely define the curvature distribution inside the element, if that's what you want, the strain and the curvature distribution. But that's beyond this. In any case, what is interesting about the kinematic matrix AG, starting from here, right, is that it appears as the derivative of these deformations with respect to the displacement. By the way, inside Ln hides u1 minus u4, u3, u5, right? Because the change of length is by Pythagoras, the square root of the sum of the squares. So the displacements, the translations are involved. These displacements are all hiding here. And here are only hiding the two rotations of the nodes. So all the 6 n displacements are included in here. When I differentiate with respect to these 6 displacements, I get exactly the same kinematic matrix. In fact, I get AG for the first time, and then when I apply virtual work, I get that the equilibrium is satisfied. Right? So this is the basis. Kinematics is always the basis. Equilibrium always follows. So I like to say in my class that the world is geometry. Right? The world is geometry. Forces follow by energy, work principles, and stuff like that. Right? Okay. So this is the original state. But in any case, it's nice that we have these two things. Okay, so here is the general idea of the rotational formulation, which we are big subscribers of, and whoever does not like to use it will be complicating their lives unnecessarily. But you're welcome to do so. Right? I have no objection to you complicating your lives if you want. By decoupling the deformations from the rigid body displacement. So basically what I have done here is I have identified the deformations, and by describing the deformations and forces relative to a system that rotates and translates with the element, I am removing the rigid body modes from here. Right? So, this is not mine. So by decoupling the deformations from the rigid body displacements, the rotational formulation affords the possibility of using small deformation kinematics to relate the strain field epsilon to the element deformations V. While, of course, we are going to use large displacement kinematics to relate the displacements to the deformations. But the most interesting part is that the strains inside the element use small deformation kinematics. So the element formulation is very simplified. The continuum problem is simplified immensely. The discrete problem remains nonlinear. The continuum problem is simplified. And the same, of course, is true for the stress field sigma and its relation to the basic element forces Q. You see, just by relating Q to P and V to U, I haven't done anything more than solve a discrete problem. Now I have to go inside the element and see what strains are the ones caused by these V's. And by doing this treatment, I can afford to consider the strains small. Okay? That's a key idea. This way, nonlinear kinematics are limited to the relation between element deformation V and end node displacements U. And nonlinear statics are limited to the relation between element and forces P and basic forces Q. So I'm only doing it at the discrete level, at the end nodes. I don't have to do it inside the element. For a class of finite elements, what does mean class of finite elements? All the 2D frames, all the 3D frames, all the plates, 4 node, 6 node, whatever. These relations, i.e. this relation and this relation, can be done once in transformation classes. Okay? So the transformation class of OpenSees, which is one of its incredible strengths, is set up once for all the frames. Right? Now this is 2-node, 2D and 3D frame elements. So you want to have your favorite 2-node element, 2D frame element, which is the fiber hinge element, or you want to have a distributed inelasticity element, or you want to have a concentrated hinge element, or whatever you want to have. If you want to turn on rotational formulation and account for large displacement, all you got to do is tell OpenSees that you want to use the transformation class corrotation. The element itself is formulated under small strain kinematics. All right? That's a big, 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 big help for those writing elements. Of course, for those using them, probably it doesn't matter. But if somebody wants to write a new element, I think it's a big help because the geometry is taken care for you. All right. Now, somebody may say, hold on here. You sound a little too cute. How do you ensure that the deformations inside the element are small? I ensure it by subdividing the structural member into as many small elements as I need. Let me show you. Here is a pinned column. Pinned column, otherwise known by the great Leonhard Euler name. Material is linear elastic. I want to determine the buckling load by computer. Now I know all of you know the answer, of course, of the exact buckling load derived by Euler. In fact, he derived it even for large deformations. There is a famous paper of his, but in any case, you know the exact answer, all right? I'm going to do it by computer because I don't believe anymore in exact answers. Because the exact is only for linear and then for nonlinear it doesn't exist, right? Nonlinear material, I mean. All right. So if I use a single element from here to here, and the element satisfies only linear kinematics, I'll get zip. Nonsense. Garbage. If I subdivide, however, the column into two elements, which is not shown here, I put an intermediate node. Now, you see, this is the deformed shape of the buckling mode. If the chord remains here, the spacing, the distance between this and this is huge. You cannot call that small deformations. But if you subdivide the column into two elements, all of a sudden your node would be here, and the straight line, the chord, is here and here. Now the deformations are becoming smaller. And if you subdivide in 4 and 8, you are getting closer and closer and closer to the exact solution. By the way, those of you who spent nights trying to derive the sine and cosine solution with Euler's differential equation, which is great, the exact answer is 2.476. With 4 elements, you would get 259, overestimating it. With 8 elements, you would get 249, and with 16 elements, you would get practically, right? So as I write here, the exact value is overestimated by 1.3% with this case here, right? So that's how we do these kind of simulations these days, right? We don't have exact answers, but by subdividing the element, we know that it converges to something that we got. All right, so if you wanted to represent buckling of elements, whether they are linear, like in this case, or nonlinear, it behooves you to have at least one intermediate node so that you can capture the rotation of the chord. If the top and bottom of the column are braced. If the top and the bottom at the bottom of the column are unbraced, so the top displaces relative to the bottom, even without subdivision, you get a pretty good answer because the chord is already rotating, right? So if you want to study the buckling of unbraced frames, you don't need to subdivide the columns because the lateral displacement is the most important effect and the chord captures it, right? If you want to be more precise, of course, you can subdivide it and spend more time. All right, so I try to illustrate basically how we capture the phenomena of nonlinear geometry. So now the question that comes is this little scheme here. I want to explain something that you hear a lot in professional practice and so famous P delta analysis. So at least this class here don't do the kinds of things I hear sometimes and drive me nuts. All right, so we have kinematics. That's the relation between V and U. I'm not talking about the kinematics of the element, right? The kinematics of the element for me are linear continuum kinematics. Small strains, small deformations in the element, in the continuum, in the discrete element ends relation, the element deformations V and the displacements U are linear, that means that the chords, the nodes, displace, rotate little. What is little? Angles under 1%. Right? Please don't give me any numbers, 5 inches or stuff like that. Never do that. Just angles. Right? Otherwise known as lateral drifts, relative displacements, whatever. Whatever your choice of terminology. Don't ever tell me the displacements are small because they're 5 inches, because I'm just going to grab a gun. 5 inches means something to you, doesn't mean anything to me, and if the structure is 300 inches or 300 feet tall, 5 inches may not be that big. Right? I don't know. I have to have a ratio, 5 over 300. So 300 times 12 will be 3600, 5 over 3600, actually it may be very small. All right? But 5 inches over 10 feet may be large. All right? So that's what this here says, right? So linear analysis says the kinematics are linear, the statics are linear, the material is linear. So that we learn, of course, undergraduate school. Everybody is kind of covered with that. And for these, there are excellent excellent linear analysis programs. You close your eyes, they model it for you. You can even have artificial intelligence model the model for you one of these days, and then you're just done. Okay? All right. The next level of response is this one here. Linear kinematics, linear statics, nonlinear material. Maybe for very stiff structures. Very stiff structures may behave like this, right? So basically they don't deform a lot, but the material is nonlinear because it fractures or whatever, and you want to capture that, and so you have this case. Right? So in that case, you will have transformation class linear, linear. Actually, one transformation class linear. One transformation class linear. And then the material is whatever you choose the element to do, right? So you can pick elastic, or you can pick concrete O2, or whatever the other names are, right? Okay. The nonlinear geometry case means that both the kinematics and the statics are nonlinear, exactly as I showed you. You would obtain this in OpenSees with using the transformation class Correspondence. That's the only transformation we have for this nonlinear large displacement, right? Okay. So you will include that if the material is linear, which is possible. Why? Very flexible structures, pre-stressed nets, slender columns, very slender structures, antennas, aerospace structures, stuff like that. They may be linear in material response, like the Boeings and stuff like that, but they undergo large displacements. All right? So for the study of those kinds of structures, that's what you need. All right, and here comes the sort of, okay, so finally I will jump from entry 3 to entry 4, which is the complete enchilada, of course, right? Nonlinear, 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 right? And that's what most of you probably will be doing. Well, actually, I'm sorry, I take it back. Most of you will be doing either this, number 2, or this. I don't think anybody in earthquake engineering assumes that the materials are linear elastic. Right? We don't have that case very easy. All right. So you will have either this or this. Now come the two cases, one of them which is that are so important, so much abused in the profession in a way, if you like. And what they consist of? They consist of linear kinematics, but approximate nonlinear statics. What does that mean, approximate nonlinear statics? You take only the effect of the axial force in the so-called nonlinear truss effect, which I wrote down here, and you include only the effect of that axial force in the deformed configuration, in writing the equilibrium equations. You don't include that in the displacements, calculated with deformations. You don't include it for the bending moments and the resulting shears, only for the axial force. So you assume that the axial forces are so much more dominant than everything else that they're the only ones that are deserved to be studied in the deformed position. that particular branch of analysis is known as p-delta analysis or second order linear analysis. Right? If it is associated with linear materials, p-delta analysis in the more general cases. It is a subject that arises from historical reasons at the time when no computers were available to try to capture the effect of the gravity loads on reducing the lateral resistance of structures. As far as I'm concerned, if you are going to do a pushover analysis, you are much better off doing this or this. Obviously, in pushover you will do this. You're much better off. I don't have time to justify that. All I need to tell you is that the stiffness is tangent. You will see what the tangent stiffness brings. In this case, the stiffness that you have is not tangent. So if you turn on Newton-Raphson during the pushover, and you have a non-tangent stiffness, and you insist on a tolerance that is very small, you're going to be sitting there forever. Right? So somebody else with a rotational was supposed to be more accurate and thus conceivably expensive. It turns out that it beats the heck out of you in speed. Much more accurate. There are some pitfalls about the rotational formulation, right? So, as I said, we can have here a discussion of several lectures, 2, 3, 4, 5. We can go through some of the other things that happen when you use the rotational. In particular, remember, something that you don't see in the p-delta analysis. This change of length in the rotational. Let me give you an example. I don't have a post here like I have in my lecture. Let me just show you what I have. I have a close approximation to a post. Let me show you something that is very important. Okay, so here is a column, right? Here is p-delta analysis for you. A column displaces laterally. For the p-delta analysis, the length of the column is the same as it was here. Right? There are no deformations. In other words, a column that was standing vertical and displaces 5% of its height is still unchanged in length. You look it up. Okay? If you don't trust me, just go and look it up. There is no deformation V1 because the new length is only determined by this displacement. Since this displacement remains the same, there is no change in length. If the column were inclined, sure. If it moves horizontally, elongates. Linear theory will become. But if the column is vertical, if displaced laterally, doesn't change. With the rotational formulation, of course, the new length is not the same as this one, and consequently, the deformation is there. Now you come along and you say, gee, trained from all these years of p-delta analysis, I'm going to restrain this degree of freedom, and I'm not going to let it come down. Just keep it up. It's supposed to move horizontally, isn't it? You restrain it, boop, tension in the column. What the heck is going on? These OpenSees guys are the biggest loonies ever seen, right? Well, that's truth, that's physics, that's nature. I don't know who the loony is in this case. As I said, it's always the question of, are you getting what the structure expects from you? Right? So this is the problem. When you go sophisticated, you've got to be knowledgeable. See, you cannot be sophisticated, pretend. You've got to be knowledgeable. Right? That requires study and care. All right. So this is one problem. This is why, if you are scared, stick with p-delta. But as I said, you're doing something that is not as good. All right, so we move on, right? So basically we got those things covered. Okay. So now I wanted to talk to you briefly. You see, I should have known, it takes me 60 minutes for 30 slides at the fastest. So I had prepared more than 30 slides. I shouldn't have worried about the other stuff. So Frank, in the future, you have to give me a whole day. If this is supposed to be, everything, right? Okay. So we have to have a whole series. All right. Maybe this was all useless, right? So if we substitute the resisting forces P that I showed you before inside this resisting equation, and we calculate the resisting forces. We have this expression for the resisting forces, and now we have something very important here. We say the relation between end node displacements for an element EL and the global degree of freedom displacements U is simply a correspondence relation, right? You know that, right? That holds under any government, under any displacements. All we are saying is that if this global degree of freedom displaces unit amount, the corresponding element degree of freedom displaces the same. That's a correspondence relation. And so if I know the displacements U, I can immediately calculate the element displacements U. From this relation here, I can calculate the element deformations V. I go inside the element formulation and I calculate the basic forces Q. Having the basic forces Q, I transform them with this AG. I sum them up. I got the resisting force of the structure. Very simple. Right? The hardest part is now getting Q from V. As I said, getting V from U, OpenSees does for you. Transformation class. Getting P from Q, OpenSees does for you. So the AG is all in transformation class. All you got to worry about now is Q and V. All right. All right. So if we can determine the resisting forces PR, we turn our attention to the solution of the global equilibrium equations, right? So unbalanced forces, applied minus resistance have to be 0. This is a nonlinear system of equations. You guys realize that. And a nonlinear system of equations is simply solved by some kind of linearization method. Right? We don't know how to solve nonlinear system of equations. All we need to know, all we solve is linear system of equations of some form, right? Simplify. Okay, and so you simplify, so you, for a function g of x equals 0, these are vector functions, by the way, you write the Jacobian. The Jacobian is the partial derivative of every function with respect to all the variables, and then you improve the original estimate x0 by corrections. Now, a key aspect of this process is the calculation of this Jacobian. All right? That Jacobian, calculating the tangent stiffness matrix and solving this linear system of equations over and over and over and over, can be an expensive proposition, particularly in multiprocessor environments. Because you have to formulate that matrix over and over and then bring it some central place where you can basically solve for the equation system. Right? As a result, competitive methods, whether they are known as Krylov methods, we're going to hear about that, or whether they are known as BFGS methods or other iterative methods, avoid forming the stiffness matrix J and try to update the solution by some other means. Right? They use the matrix occasionally, but they don't use it all the time. All right. So keep that in the back of the mind. So there is a lot of work here. And I hate to tell you this, but I know too little about it. Right? So you can be an expert in elements and still survive by having Frank or Michael or some others write the solution strategies for you in OpenSees. Right? All you got to do is have your ears on the ground. Listen. Say, oh, he says that maybe this method for this thing can be done better. Nobody's going to come and just put it in your door. You have to kind of inquire. Is this the only method of solving nonlinear system of equations? It isn't. OpenSees has several strategies. Okay, I'll skip this thing here quickly. Okay. And I wanted to come to something that you may want to just keep in the back of your mind. So, as part of this method, assuming that I want to do Newton-Raphson, because I want to tell you a few things about Newton-Raphson, since I have worked almost 20 years with Newton-Raphson, very little else, so I have a little experience with that, maybe a little more than some of you. But there are people in this room that have a lot more experience with other methods as well, because they were like Frank and Michael and others, right? So you talk to them if you have questions about the solution strategy. All right. The Jacobian requires that you form the partial derivative of the resisting forces PR with respect to the displacement U. How are we going to calculate that? Partial derivative of the resisting forces R with respect to displacement U. All right, let's go look at it. Okay, well, we said that the resisting forces are Boolean matrix times P. The P is simply AG times Q. So taking the partial derivative of this with respect to U means chain rule. Taking the partial derivative of this with respect to U for each element, because clearly this expression only depends on the U of the element, not of the U of the structure, and then doing partial derivative of U of the element with respect to U for the structure. That gives us, oops, yeah. So I timed it pretty well. I think this guy is going to, 9%, I think he's going to let me go for a little more, and then he will quit. All right. So the partial derivative of this with respect to U, right, gives you the element stiffness matrix. This is the Boolean matrix, one more time. So all what you're doing here is basically taking the tangent stiffness of the element and assembling it inside the structure and adding it up, right? So it's global stiffness assembly, straightforward. Okay, now let's look at the partial derivative of AG with respect to U. AG is a function of U. Q is an indirect function of U because it depends on V, which depends on U. All right, so I differentiate first AG with respect to U while keeping the forces Q constant. I differentiate then Q with respect to V, V with respect to U, and I get the geometric stiffness of the element, geometric stiffness of the element first, and the material stiffness second. So another nice thing about the rotational formulation is I can cleanly split the material stiffness from the geometric stiffness. This I only have if I have large displacements. This I have always. Right? Otherwise the structure is unstable, of course. If I don't have stiff material and geometric stiffness, I'm in trouble, right? But I can have geometric stiffness and no material stiffness. Think of a horizontal prestressed cable. With a high prestressing force here, I have stiffness in this direction. All of you guys know about this, right? If you stretch a cable and step on it, it's not going to collapse. There is a stiffness. All right. So the element stiffness is the sum of two contributions, geometric and material. This is the basic element stiffness K, and all right. So in the remaining 5 minutes, the Newton-Raphson algorithm requires that the current tangent stiffness matrix be used at every iteration of each load step. Otherwise, it's not called Newton-Raphson. Classical Newton-Raphson. So this ensures quadratic convergence. You can look up and see what that means. By the way, we will try to post these things in case they are useful to somebody. So be a little patient for me to generalize it maybe tonight and tomorrow, and then we'll post a slightly better version. Depending on the size of the problem and the available computer architecture, this may be a very expensive proposition, as I said earlier. Consequently, the following variants, and I think Michael was instructing me before that I should have a third variant here, which are these Krylov methods, which don't fit neither in the quasi-Newton nor in the modified. They're called accelerated Newton-Raphson methods. Third category. Right? I was always putting them in here, but I stand corrected. And I say we discuss this briefly next, I'll skip that. There are variants of the Newton-Raphson algorithm, okay, blah, blah, all right. No matter which method you use, the way I presented the algorithms before, you will see them posted. I didn't discuss them with you because I'm sure you probably know what a typical Newton-Raphson algorithm looks like. The issue is that you are not going to do a single step. You're going to apply because you're concerned, first picking the starting value, the initial guess, and secondly, how big of a load can you apply before starting the process. That's the biggest scare of people with nonlinear methods, right? How much of a load can I put on the structure? Will it collapse with this load, right? And so, to avoid this problem, what you do is, first of all, you always run a linear analysis first. get to know your structure, right? So I don't hope nobody's in here who is going to attempt to run a nonlinear analysis without having run a linear analysis first on a structure, right? Now I understand that some software out there discourages you from doing that because they have different inputs for linear versus nonlinear. And you cannot use the same things. Okay, look at that. So basically what do we do here, Frank? Now can we use your famous computer? You're going to let me talk 5 more minutes overtime, or otherwise I can shut up also.
No.
I'm close enough to...
We're close to the picture part.
I know the picture part that they may want to see.
That's the point.
They may want to see the picture part. Okay. So what are we supposed to do? We're supposed to do this. You do this. Yeah. Here you only need the PDF file, so it's good. You almost had it. In fact, didn't you copy it in that thing?
Yes, it is.
So you just launch it from yours.
I will.
So you don't need the thing.
I don't need much.
Yeah, you don't need the...
No, I was working on something else.
Yeah, no, I know it. I'm just saying. I can just stick this in and see if that famous device works. So be sure to give me feedback, right? Whether this is any useful or whether this is all useless. Then in this case, if useless, we'll just put it in a garbage can, which is legal. All right, great. So you just do. Right, if I take this out, can I take this out? Take this out, and this will put here. So I go. Excuse me for this. What do we do here? Otherwise I'll just do click down. Just click here and see. And say down. Okay. So let's go page down. Where is page down in this fancy computer? Here. No? Okay. Can we have a full slide, please? Here. Control L.
Control L.
So how do you make it big so it fills the screen?
Sorry?
Down the very bottom.
At the bottom of that screen?
Menu.
View at the bottom. View.
Or edit.
Oh.
Maybe it was edit. Oh, now it
And oh, good. Things. Yeah. Fantastic. Okay. So to ensure that the process converges, we have to use a small enough step size. And because we have no way of knowing that step size, other than having run a linear analysis before, but even then we may not be able to quite assess what's going to happen, the best thing is first, you're going to do a multi-step incremental analysis, and secondly, you will use some kind of load factor control. It is not wise with a nonlinear structural response to run any kind of automatic solution without load factor control. Now, in OpenSees, load factor control is understood as displacement control. And of course, displacement control, which displacement? You have to specify the degree of freedom you want to control, and blah, 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 blah. Right? It's not necessary that it only be displacement. It can be energies, it can be other things, but many people call it displacement control. I like to call it load factor control, for the reasons I just illustrated. All right, so now here comes an interesting thing I like to tell my students in nonlinear analysis. First, the black line, numerically exact solution, doesn't exist. Only for 1 degree of freedom system it exists. For any other system, the black line is the projection of the n-dimensional response of your end-of system onto the plane that says vertical translation, load factor. So your actual solution, which is these red dots, for multi-degree of freedom systems may end up actually above or below. So the graph is meaningless. But we show this kind of graphs for one-dot systems so that people appreciate what it means to run a Newton-Raphson algorithm, right? And so here is a detail. Bing, tangent, bing. Bing, tangent, bing, bing, tangent. You won't be able to see such a cute graph with a red dot ending up on the thing if it's a multi-degree of freedom system, right? Because the answer is somewhere else in the end of space. You are only monitoring the vertical translation. All right? And finding that exact response for the vertical translation means that all the other displacements have to be 0. That's not what the response gives. All right? So I think about this, and so you won't be able to have this kind of cute plot. But in any case, it illustrates the main point. So let me show you a few things that I wanted to show here, right? So this is Newton-Raphson, 5 steps. This is Newton-Raphson, 2 steps. This is no iteration, right? Apply the load, accept this answer. 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 Wow. In other words, I don't insist on corrections. I just say I'm happy with the red dots. Somebody may say, wow, what a stupid method. Right? Only the initial stiffness is one linear step. In other words, linear step after linear step, but updating the stiffness.
It always converges.
Huh?
It always converges.
It always converges. And if the small step is if the step size is small, it is pretty good. And when is the step size very small? When you run an earthquake motion. Because your bloody accelerations are every 0.005 seconds recorded. Right? So if the step size is small, so many people run dynamic analysis without correction. Right? So don't get hung up on these iterations that I'm showing here, because it may be good enough just to do this. All right. Now, if we only update occasionally, then it takes 4 iterations to convergence and 5 for the second. By the way, if you have a program that doesn't, Newton-Raphson claims it uses Newton-Raphson, it doesn't converge in about 4 iterations, then you know something is over. 4 or 5 iterations has to converge, otherwise there is something going on in there, right? Something fishy going on. All right. So I'll skip these quickly, and I want to come to this process. So suppose I want to simulate the response of a structure that's going to come up here, come down, and snap, or soften and fade. To simulate this response, you need, as I said, to ensure that you don't apply the same load consistently. You want to have load factor control. You want to adjust the amount of load you put on the structure as a function of the softer response. To be able to do that, you need to turn on displacement control or arc length methods or some kind of adjustment of the load factor, right? So typically we assume we multiply lambda times p. That lambda has to be adjustable. If it is adjustable, I can walk all the way up to the top of the hill. I can determine the ultimate load. Very safe. I cannot just go beyond, unless I also have control past the peak, which displacement control ensures, arc length method ensures. And in that case, you see what happens, right? You apply a huge time step, and instead of the process seeking a solution at this height, what displacement control says, I don't insist on you applying this load. I am happy if you reduce the load and hit this point. I apply this load, I realize I can't get it, I adjust the load and end up here. So instead of insisting that the load be maintained and that the structure rises to match the load, all the load factor control does, or displacement control does, is it accepts you to reduce the load so that you can end up on this softening response. You can only do this, however, if you have one load pattern that varies. You cannot do this with multiple load patterns. Right? So look at that. You see 39 pages takes 60 minutes. So Frank, next year if I have to talk about sections and elements, I need at least 2 more hours. Okay? I'll work on it already so I don't have to rush it on the moment. I hope that this was marginally useful. I don't know, as I said, I'm trying to condense here about 10 lectures of nonlinear analysis into one. Are there any questions at this point? You can always write to me. By the way, you can also send me anonymous emails, I suppose, right? Something you didn't like and you don't want me to identify who you are.
OpenSees users anonymous?
Yes.
Send them to me and I can,
Yeah.
I'll send them to him.
But you're going to give back feedback, right? You're going to write evaluation, so tell us what we need to do next time. Because as I said, Frank and I would like to enhance this with some OpenSees examples. And we would like to present also sections and beam column elements and stuff like that, which I had prepared, but there is not enough time to go through. So maybe I spend too much time on this. If you don't like this, we can do something else. All right? Okay.
Thank you, Professor.
So thank you.